Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Hello and welcome to problem 56. If you've ever thought to yourself you wished you could do a problem that had about 8,000 parts to it, then 56 is the right problem for you. So in this problem, we have a golf ball that is dropped from 9.5 meters in the air. It hits the ground and bounces up to a height of 5.7 meters before it falls 4.5 meters towards the ground where it is caught. This question wants to know how long does this golf ball actually spend in the air? Since there's three different parts of this golf ball's motion, we need to do at least three different kinematic calculations to figure that out. So a few things I want to set up here. I'm going to draw a little sketch of what's actually happening for this one. Here's my golf ball. Phase one is the golf ball falling to the ground. It then hits the ground and bounces back upwards for phase two to some height that's not quite as tall as it started at. It then falls down towards the ground to its ending point right about here. Now, since most of the motions are pointing downwards, since most of my displacements are going downwards, and because acceleration is going downwards, I'm going to define my directions as anything in the downward direction is going to be positive, and anything that is upwards is going to be negative. Now, if you solved this problem and just switched that around and went the other way, you'd end up with the exact same answers we're going to get. But because there's so much more downwards motion in this problem, it's going to reduce the difficulty, or at least the irritation level of these problems a considerable bit to call downwards the positive direction. So with that, and I'm going to keep my color coding here for which section we're in, let's talk about the motion during part one. We know the initial velocity is 0 meters per second when it is dropped. We also know we're on Earth, so our acceleration is 9.8 meters per second squared downwards, which is my positive direction. And we know it's going to fall 9.5 meters down, which again, the positive direction, before it hits the ground. Now, my goal here is to figure out how long it spends in the air, so I want to know t. Now that means I know my four variables there, or I know three of them rather, and I'm looking for the fourth. The final velocity is the variable I don't know and don't want to know. So when I'm picking which equation to use, I'm just looking for the equation that does not have that final velocity in it. So to solve this, we start with x equals v naught t plus 1/2 at squared. I'm going to get my helpful little diagram here out of the middle so we have some room to actually solve this. So, do this again, x equals v naught t plus 1/2 at squared. When I plug in my numbers for this first one, we have my distance of 9.5 is equal to v naught t, which since my initial velocity is 0, that whole term goes to 0, plus 4.9 t squared. Then that gives me a t squared value of 1.94 and a t value of 1.39. Now that's just the time for part one of this problem. My goal is to figure out how long it'll take to do all three parts, but hey, we're 1/3 of the way there. So I'm going to tuck this off to the side, and let's do the same thing again, but analyzing the second piece of the motion instead of the first one. So the second one has a few things that are a little bit different. First of all, we know its final velocity because it's bouncing upwards. Its final velocity is going to be 0 meters per second because when it reaches the top of its bounce, it comes to a complete stop. We know the acceleration is 9.8 meters per second squared. And we know the height it bounces to is 5.7 meters. Now, tricky part here, that's 9.7 meters, or I'm sorry, 5.7 meters up. So it's a negative 5.7 meters because in that part of its motion, it is moving upwards 5.7 meters. Okay, now before I can figure out my time, I do need to know what the initial velocity actually was. So we get to do two calculations for this one. My first one, since I don't know what t is, has to be done with the v squared equals v naught squared plus 2ax equation. And when I plug my numbers in here, we get 0 equals v naught squared minus 111.72. Then when I rearrange this, we get v naught squared equals 111.72 and square root it to get a v naught value, our initial speed of 10.6 meters per second. Okay, so I now know my initial speed. And that lets me use the equation we used before, the x equals v naught t plus 1/2. Actually, we can do this with a nicer equation now that we know more parts. Let's just use that first easy one, v equals v naught plus at. This gives us 0 is equal to 10.6 plus 9.8 t. Oh, and that 10.6, because it is an upwards velocity, is also going to be the negative value of it for us. That's negative 10.6. When I then subtract 9.8 and divide by that, we end up with a time value for the second part, time 2, of 1.08 seconds. And that is the final time for this second chunk. So 2/3 of the way there. My last piece here, so let's again add in another setup here, is talking about the return fall, where it falls a certain amount before it gets caught by a child. So its initial speed is where the second part left off. Its initial speed is 0 meters per second. Our acceleration, 9.8 meters per second squared. And we know it's going to fall 4.5 meters, which, since down is our positive direction, is just positive 4.5 meters. Since my goal is to find time, we're going to use that same equation one more time. X equals v naught t plus 1/2 at squared. Since v naught is 0, we have 4.5 equals 4.9 t squared. So my t squared value becomes 0.92, and my t value, when I square root both sides, is 0.96 seconds. Okay, so I've done my 3 parts. I have my three separate times calculated, which means all we need to do to finish this problem up is find the summation of my times. And that gives us 1.39 for the first chunk, plus 1.08 for the second, plus 0.96 for the third, and that gives us our total time of 3.43 seconds is how long this ball is actually bouncing in the